Welcome to EVE, the Environmental Vegetation Evaluator, by Team 2, Awesome Products Incorporated. The problem our team encountered was that many farms are subject to various hardships, including changing environmental conditions, harmful pests, and falling behind on rigorous upkeep. Team Awesome Products Incorporated is developing a team of robots to aid landowners in the identification of these events. Currently, there are no commercially available robotic solutions to combat agricultural pests and monitor atmospheric conditions. There are some organizations that are developing solutions to these problems, though they are far from perfect. Many conceptual designs are relatively large, utilize poor quality components, or are severely underdeveloped.
Hello, Josh again, and I'll be running you through the market slide. So with 40% of the United States being farmland, EVE is really targeted towards commercial and local farmers. By utilizing EVE, we're able to help promote the health of human-grown vegetables. Our primary focus is with commercial, recreational, and organic farming so that we can increase the yield of crops output. Now, with this larger yield of crops, we can see secondary effects with both supermarkets and product supply companies, as well as tertiary effects to the local population.
The design requirements and criteria for EVE are as follows. For the requirements, EVE should be able to cover a 100 foot by 100 foot square area within 10 minutes. Each robot needs to be mobile. They need to be able to visually identify plant decay and pests and bugs. They need to be able to test atmospheric conditions as well as traverse rough terrain that you may find on farmland and fields. The criteria for EVE is that they are reliable, cost-effective, environmentally friendly, utilizing sustainable materials and solar renewable energies. They're tailorable to farms, convenient and easy to use, and are repairable by the user. Now, I'd like to introduce you to the EVE project. We have 4 drones as part of this project. The temperature drone that will take the temperature above the crops, the temperature and humidity that will take below the crops, our soil moisture content measuring drone, and a pest detection drone, all of which are individual drones that are ground-based and will traverse the farm. The pest detection ground type will not be displayed in this presentation due to extenuating circumstances with one of our team members no longer being a part of the team.
Hi, my name is Chloe and I will be presenting the air temperature robot for the EVE project. The mechanical design of this robot utilizes a pulley system that extends a temperature sensor, as seen up top here, above crop foliage. It does this with a single DC hobby motor and a 3D printed spool, which will pull a durable paracord string up and down, spinning it on the spool to extend and retract the pulley. When the pulley is in action, there will be 2 feet powered by servos that stabilize the robot to ensure that it does not fall during the reading. There will be an acrylic casing around all of the important electronics around this robot so as nothing gets damaged by robot or terrain, and it will operate on a 4-wheel drive system using 4 DC hobby motors as seen here. In the circuitry of the robot, here we see the 4 motors that power the drivetrain, the single motor for the spool, all powered by L293D motor controllers, and then the 2 servos for our feet, an ultrasonic distance sensor for navigation, and a temperature sensor which will be at the top of the pulley. Additionally, we have the Arduino Uno as the brain of the robot, and 2 batteries here. The robot will operate according to this flowchart. It will initiate and then read to see if there's any input from the other team robots. It will then read the distance. If it is less than 10 inches, it will turn left and read the distance again. If it is still less than 10 inches, it will turn all the way to the other right and read the distance again. If it is still less than 10 inches, it will output assistance needed to the other robots. If the answer is no to the less than 10 inches, it will move forward, read the temperature according to a time-based system, and then loop the cycle again. Similarly here, it will follow these steps to go around the object for both turning left and turning right. If the distance is not less than 10 inches, to repeat the same cycle. Here is the code for the robot, where we see initially we start setting up variables and the input-output of each pin in the code, and then defining our functions here and here, and then the execution loop that the robot runs on. Now I will demonstrate the functionality of the circuit here in Tinkercad. As we can see, this is my circuit here and the code, briefly scrolling through that. And then we can start the simulation. We'll set the temperature a little low and the distance is at 41 inches. So we see that it read the distance at approximately 41 inches. It continued to move forward and then currently is operating the pulley with the feet down. It read the temperature here and then it's retracting the pulley and then the feet initialize again and then the motor start. If we decrease the distance, we see that it is currently reading temperature, so it won't do that. Now we see it going around the object using the turning systems and then redoing the whole cycle. Then we start again and it'll continue to do that whenever there is an object.
Hello, ladies and gentlemen. My name is Josh Jeanette, and I'll be running you through the ground temperature and humidity robot. As seen here in our mechanical design slide, we have a top, right, front, bottom, and a top left view of my robot. Now, located on the top portion here is the solar panel. By adding a solar panel, we're able to extend the battery life of this power source located directly behind it. Underneath the solar panel is our Arduino unit. This is used to control all of the processors. Well, directly below that, we have the servo motor. And as you can see from the bottom view, the servo motor extends past the bottom of the robot and connects directly to the front axles, providing steering for my robot. To the front of that, you see our ultrasonic distance sensor. This is going to help avoid any collision with objects out in the fields. Located on top of this mast, we have a DH22, which will read temperature and humidity. Now, for the purposes of this exercise, I switched the DHT22 with a TMP36 that only provides temperature readings due to the limitations of Tinkercad. Directly behind this temperature and humidity sensor, we have our DC motor. Again, the DC motor protrudes below the body of the robot. Both halves of the axle are connected directly to the gearbox. This will provide constant power and even power to the wheels to prevent veering off on one direction or the other. Next, I have my circuit design. The circuit design here is laid out how it is on the robot. Directly to the front of the robot, we see this ultrasonic sensor. Directly behind that is the servo connected to this breadboard. Breadboard is controlled by an Arduino unit and supplement power is provided by a 9-volt battery. Directly behind that, we have the TMP36 sensor as well as the gear motor. Directly to the right, I have a few lines of my code included in. Here are some code snippets that I have for my actual operation. Up top, we can see the drive motor, steering, ultrasonic sensor, temperature. I separated these out into sections for ease of reading. Directly below that, we have the void setup. And below that, we have a bunch of my definitions that define some of the functions used by this robot. As we can see here, I have the code and logic flow of my robot. It starts by getting a start command or a startup command that will set the wheels into a 90-degree or straight orientation. From there, it reads distance and determines whether or not the path is clear. If it is, the robot will continue forward and conducting its temperature and humidity sampling. This process is repeated back. If the path is not clear, the ultrasonic sensor detects whether the object is within 10 inches of the front of the robot. If it is, the robot conducts the object avoidance command. This entails turning 90 degrees, moving forward, turning back 90 degrees, and testing to see if the path is clear. After the path is clear, the robot then returns to its original path.
Hello, I'm Justin. Today I will be introducing the soil moisture sensing robot from the EVE project. For the mechanical overview, we went with a robot design that incorporated a tracked drive system. This drive system will allow the robot to traverse many types of terrain with ease. The robot itself will be approximately 30 inches long and approximately 16 inches wide. The vehicle will also be approximately 15 inches tall to incorporate a high visibility safety flag for ease of spotting over the crop foliage, as shown here. Each track will have 2 DC motors powering main drive wheels, providing plenty of power for the vehicle. Each motor per track will be electronically connected so both motors turn at the same rate. The unit will be powered by a large solar panel roof mounted on top of the vehicle, as shown here. This will be its main power source with a battery backup. The soil moisture probe will be housed in the center of the vehicle and deployed via servo under the chassis to take readings. The servo will then retract the probe back into the vehicle to prevent damage. The vehicle itself will be run by a single Arduino, as shown here. This is where the servo and soil moisture housing assembly is. Battery backup will be located on the rear with your solar panel on the front. In the circuit design, we had to incorporate a way for the vehicle to see where it is going and also deploy and retract the sensing probe. We used an ultrasonic distance sensor mounted on the front of the vehicle for navigation purposes. This will provide input to Arduino to use to decide on navigation commands. We also incorporated blue LEDs to indicate when the track is moving forward and red LEDs for when a track is moving backwards, as shown here. The DC motors are controlled by a microprocessor chip, which for this demonstration is powered by 9-volt batteries, as shown here. Arduino utilizes C++ coding. Provided here are a few snippets of the code that the vehicle will utilize to complete its task. I have shown the variables declarations here, some various methods that control the tracks, which is shown here, how this vehicle senses and interprets distance, which is shown here, and how the vehicle deploys and reads the soil moisture content, which is shown here. The vehicle will receive orders either from a central hub or other robots in the project to execute specific tasks. These tasks can be periodic monitoring of the soil or to report to a specific location called out by the other robots. Each robot is able to send, receive, and store information from one another to operate. Once the vehicle receives its orders, it will determine if the path is clear. If the path is not clear, it will perform various maneuvers to check distance, to navigate around the obstacle, as shown by this flowchart. Once the path is clear, the robot will continue on to its destination. Once it reaches its destination, it will deploy the soil moisture probe and get a reading in percentage. After completing its task, it will turn around and return to its staging area or execute the next set of orders. Allow me to provide a short demonstration of the working code in Tinkercad. As you can see here, I have my circuit loaded up in Tinkercad along with all of the code required to run the vehicle efficiently. I will start the simulation. It's going to await orders. I'm going to tell it to go to target. So orders have been received and it started moving, as you can see by the blue LEDs. It's going to now sense that there's an object in its way and is going to perform its object avoidance programming methods to go around the object. It is then going to sense if it has passed the object. And at this point, I have moved the object out of its way. So it's going to move forward, and it'll then turn left to see if it has fully passed the object. As you can see by the reverse indicator light and the forward indicator lights, the path is still clear. So now it'll move forward back to its original path, turn right. As you can see, again, with the blue LEDs indicating forward, and the red LEDs indicating a backwards direction. Once it reaches its destination, the servo will actuate, deploying the probe. The probe will take a reading, in this case, which is 64% soil moisture saturation, and then it's going to turn around, again, as indicated with alternate LEDs and forward LEDs. And it'll head back to its staging area or execute further orders.
Our robots, while they are still a team, do operate relatively independent from one another in their processes, aside from the fact that they transmit and receive data between each other and the overseer, who will respond in case of issue accordingly to ensure the system runs smoothly.
Hello, ladies and gentlemen, Josh Jeanette again, and I'm going to be running you through the entrepreneurial aspects. So as you can see here, I have priced out all of the robots involved in our swarm with the total cost down at the bottom. Now, each robot's material costs are low compared to the labor involved with actually constructing each robot. The total materials cost of $720 and a total labor cost of $1,700 brings our total cost for our swarm to $2,420. Now, we were unable to find exact comparisons for our robot, but we did find a crop surveying robot, which of a larger size, however, didn't provide the same sensors as we're providing. The pesticide spraying robot was a larger robot that attached to a tractor's PTO, so it was unable to be used autonomously. The land survey drone costs upwards of $8,000, but again, did not provide the same ground temperature and humidity and soil moisture readings that we see with our robots provided. Some of the unique features are that we were the only multi-robot package on the market. We also had a lower materials cost compared to all the other comparable robots. Our robots are independent of machinery, which means we have minimal operational resources and staff required to be able to assess your land. Also, our robots are scalable, which means that we can use them on a private farm or a large-scale commercial farm.
In summary, EVE is designed for the farmers who require assistance maintaining their fields, have pest problems, or just want to gather quantitative data about their crop and field and the health of the farm overall. Consisting of 4 uniquely different robots, at a minimum, the farmer will be able to cover more ground more efficiently. With each robot having a dedicated purpose, multiple parts of the field can be measured at the same time. Since each robot specializes in a specific type of measurement, they can individually cover more ground more efficiently than a single robot that did the function of all 4 combined. The information gathered from each robot can be shared between each other and also shared directly with the farmer. Investing in EVE is investing into the future of farming as an industry. Increased productivity, efficiency, and the health of the crops leads to lower pricing for produce in markets and higher profits for the farmers and distributors associated with the industry. These are just some of the references we used throughout this project to develop and create our robots. Thank you very much.